Recording. All right. Welcome back to this course. Before I continue, I want to ask you here in Skellefteå and also in Zoom. So, what was the topic of yesterday's class? What did we talk about yesterday? Hmm? Hello, guys. Good morning. So yesterday. So what did we talk about yesterday? Is there any meaning that we continue today? Because it's kind of built on what we discussed yesterday. So let me ask you one and one. What did we talk about yesterday? Huh?
I wasn't able to attend the class. Sorry.
Why? Huh?
That's something that.
Like what? Maybe next person. So what did we talk about yesterday? Why?
I was working on the one. I was there.
And?
On the side, but I haven't looked through it again.
So let me just make a poll of opinions in the Zoom. So let me ask. In the order, Dima, Farouk, Kim, and Stefanos. So what did we learn yesterday? So can you unmute yourself, please, and speak up?
Sorry for yesterday, but I didn't attend yesterday.
Why?
I was have appointment for my kids at the morning.
Okay.
So I'm so sorry, and I don't have the time still to see to watch the lecture again. But I am planning to watch it today, actually, after the assessment.
Okay. Farouk?
I won't lie. I thought it was 10:15 like usual yesterday, but I didn't find anyone online.
But you saw that there is a recording, right?
Yeah. But we were preparing for the assessment today. We have assessment on 13. So me and the group.
Kim?
Yeah, can you hear me?
Yeah.
I was not in the lecture yesterday either.
Okay. So then we have a problem here. So how can you understand the problem of detection of attacks and federated learning if you don't know the material from yesterday's class about what federated learning is? We are in the theory module where you're supposed to focus on the theory. Yeah. Yes, and that you need to prepare during the practice week. I think we are kind of approaching some, well, we are in the middle of the course.
I mean, it's the same with exams, you know?
Yeah.
We study till the night before. Gonna end on Sunday evening because the practice week is over. That's just the reality.
I don't know.
This?
Yeah, I don't know. It depends on how you structure the studies. No, but I mean, I'm just wondering, I mean, how can we focus on, I mean, shall I repeat the yesterday's class then? What's the point of today's class? I mean, for me, coming all the way here, for example.
With these lectures, generally, I don't have them in my head after the lecture. You know, I can listen, but most of the stuff I need to read through again to understand.
Okay. I got it. All right.
I think I will summarize some of the key aspects of federated learning in my presentation also. So.
Okay, all right. Then let me restructure lecture a little bit. Again, so my part is a short one, so I need to go to another appointment in 45 minutes. So we start with this slide. Again, so let's make it as a recap. So what do you see here? Can you be a little bit more interactive? You're in Zoom, please help out. What do you see in here?
We see the network, and we have an input which
Yeah.
goes through all the layers.
Yes. Okay.
To the output, where we have labels from 0 to 9.
Yeah, in the case of MNIST, right?
Yes.
And this equation in the upper right corner, what is it? What is it about?
Soft marks. This is soft marks.
Mm-hmm.
Yeah. This is what decide if the pixel match or does not. So it's allowed to go to the end or rejected.
Okay, roughly. So, well, it's a normalizing function that produces a distribution of possible answers. So depending on your output, so for example, if you have 10 outputs, it gives you a distribution of most probable or a probability distribution of answers for each of the outputs. Okay. So basically, the classifier would choose the output with the highest probability. So are we fine on that?
Yes.
Good.
Then we have back propagation, which
And
try
then
to adjust the weights.
Exactly. Yes.
To reach the goal. And we go on and on and on till we get the results we are aiming for.
Yes. Yeah. What we talked about yesterday is next level of training. So where this kind of structure is learned, is trained on data, which is, well, basically on the input, which resides in different organizations. Compared to the case where all input data resides on your own on a single computer, like what you did so far in labs 1 and 2. Okay. So it means that part of data, for example, so you can take a use case where you have several hospitals specializing on different aspects, different diseases. Maybe people are the same that goes to these hospitals and they want to build a model predicting, for example, a specific disease, or I don't know, I mean, for any other useful purposes. And then the question is how you organize the training in this case. So, and when you will see the recording, so there are several options. In one option, so these organizations, they share features. What is features, by the way? I mean, can you kind of point out the place where you can talk about features of data on this on this picture? So when I say features, so which part of this picture I'm talking about? Huh?
Yeah, input, yes.
Exactly. So each of these circles that you see in the input, the other word, the synonymous to or another term to the input data is feature. So it's a feature vector. So it's a characteristic of the input. So what is a feature if you have an image? A feature. Pixels. Pixels on certain position, the intensity of pixels. If it's a colored picture, image, then you have 3 intensities for RGB, right? So these are features. That's what you input to the network. So now, features can be different, of course. So it can be tabular data, like age, disease, name, etc. So these are also features characterizing certain, case that you want to build a data-driven model on. So what I'm saying is, again, as a part of recapitulation, there are several cases, use cases for so-called federated learning. So federated learning means that you have data, input data residing in different organizations, and but you still want to train a single model. So three types of federated learnings exist. One is horizontal federated learning, vertical federated learning, and transfer federated transfer learning. Horizontal means, so now I am coming back to what I started to say, is that organizations share features exactly. So it's different individuals, but features are exactly same. An example would be if you take your beautiful MNIST data set with digits. So you have all same format, but one organization owns records about numbers 1, 2, 3, another 3, 5, 7, etc. So the samples are different between organizations, but the features are the same. In the vertical federated learning, the samples can be same, so it's all the same person that presents in different organizations, but features could be different. Why? For example, we are talking about use case of bank and a shop. So in the bank, you are characterized by your salary or your income, your household expenses, etc., mortgages. On the retailer side, you are characterized what you buy normally. So, but you are all the same person, and you want to basically build a model that jointly use this data to predict something. So this is a vertical federated learning. So you need to align the features and train the model. And then there is a transfer learning. That's a different story. You can check it in the recording. But the point is that we now want to train this structure, this artificial neural network, based on different inputs. And what you don't want to do, you don't want to exchange real data. Why? Because it is sensitive. So, and that's very easy to understand. So that, for example, in the medical case, different hospitals, they don't even share information between each other, between different units about you. So it's forbidden by the law. And not talking about a case where you have organizations in different sectors, so socioeconomical sectors. So that's why people invented this concept of federated learning. It means that each organization will train a part of the model. It will communicate this part of the model to a central server where all these partial models will be added together. And yesterday we discussed different options on how to add together different parts. And again, perform the high-level optimization, return the model to the clients. They do continue learning on their data, return back, and in this manner, so it's a kind of distributed backpropagation. So at the end, you have a single model trained on the data from all the organizations without revealing the data. And then, as I said, so there are different ways on how you combine the model, so that we discussed. So what is the problem here? I mean, now we talk about security aspect. So what are the problems? What could be the problems here? Knowing the content of the previous modules. What could be potential problems or extra problems which are imposed by this distributedness of learning? So, okay, we go back to the problems with the standalone or centralized learning. So what are the problems with security problems there? So these are the modules you have already passed.
Maybe the leakage of information.
Yeah, more leakage of information, so like privacy risks, yes. What else? So what are the main threats, security threats associated with machine learning and artificial intelligence models?
Can you manipulate the accuracy in some way? I mean,
you in Zoom, you also can help me out answering this question. So what are the main security threats? So this is a question. So we are still on this picture illustration.
if you think of the topic of the lecture, out of distribution detection.
No, well, but I mean, even before out of distribution. So what are the possible threats? You're an attacker. What do you attack in here?
In this case, the input we're trying to get the data.
Say again?
The input we're trying to get for the input.
To do what?
To bring the model to release internal data or wrong, not wrong, but
Maybe advertisal examples, the evasions attacks.
Yeah. So what is the goal with these attacks? What do you achieve with these attacks?
Attackers slightly modify input data.
Yeah. To do what?
So the model is misclassified.
Exactly. So you want to alter the functionality of your model. So you want to modify input somewhat so that it produces wrong results. So that's one thing. Yesterday, I also was talking about another target with these attacks. I mean, so far you worked with classification tasks, but in many practical cases, you are less interested in the outcome of the classification. Rather, you're interested in understanding the trends. For example, so your model should reveal that if you, so how a change in input results in the change of output. So for example, an increase in the mortgage value results in the risk of not paying it. So this analysis can be done by additional methods, which is called explainable AI. So you can perform this analysis and enable this kind of information. So your adversarial attacks may target this mechanism so that explanations are wrong. In either case, you want to mess around with the data somehow, I mean, at least as a first option, to with a goal to alter the behavior of the model so that the model become less useful for the owner. When you talk about federated learning now, as I said, the main functionality, again, on the hand waving level, so you have partial models residing in the clients, and you send them. So what do I mean, by the way, when I'm saying that you send a model? So what am I saying? So again, I mean, we stick to this picture. So what if I'm saying that I'm sending a model? What am I sending to the server based on this illustration?
Like it's like you already classify features of the model, then you send to like in a network to be processed.
No. I'm saying I'm sending a model. I'm not sending a result.
An asset?
Say again?
An asset?
A set of what?
It is an asset.
Asset. What is an asset? Hi there. Yeah, okay. Let me ask you once again on this, based on this figure. So, what are those blue circles you see? What is it? Huh?
Features.
No.
Activation functions.
What are activation functions? Example. Can you give me an example? Guys, can you give me an example? What are activation functions? What activation functions you know? Eh? ReLU. Okay. So non-linearity. So this lines, this from circles, what are those? Yeah, it's connections characterized by weights. So an output from one function is connected to the input of another function with some weight, right? It is weights that you modify during the training, gradient training, right? And these activation functions, well, ReLU is the outer function. It's a nonlinearity, but inside it's a weighted sum of inputs. So if you take now all these lines, so that that are coming from so the inputs coming from all the well, let's call them neurons. So they are neurons by definition. So they're coming into here. So what is happening here is a sum. So you sum them up, but with different weights. It's a weight multiplied by the well, the output value in this case. Are we clear here? Right? And then you apply a nonlinearity, ReLU or sigmoid or whatever inside here. But now I kind of calling to your memories of lab 1. So how these weights are represented in the implementation? How these weights are implemented, weight operations. So lab 1, part 2, backprop algorithm. Yeah?
When you create those neurons.
Yeah, you start with randomly, but with random initialization of weights. But I mean, how they organized internally? I mean, what data structure you use to implement this operation, to implement artificial neural network? So is it just the individual variables? So you have like hundreds of individual variables that keep track of all the weights, or what is it? Huh? It's matrices. So all this network, so this graphical construct over here, it is a matrix. Matrix saying that, so in the rows of the matrix is where this line comes from, and in the columns where this line goes to. And the element is the weight. Are you with me here? So you have a matrix. So in this case, it is a square matrix. Sometimes it is not square matrix, but so in this case, so you have the same number of inputs and the output. So it will be like a square matrix. So one goes to one. Well, there is no connection to itself. It is 0, but then one goes to next input. So with some weights, etc., etc., etc. So you have a matrix of numbers. By saying that you are sending a model, I'm saying that you communicate matrices of weights, or alternatively, you can communicate matrices of gradients. So gradients, those are values of derivatives that shows how the weight should be modified to minimize the error at the end, at the output, so this loss. So now, knowing what is communicated, so what is the risk here? Again, I'm not calling, of course, if you didn't listen yesterday's class, I mean, you don't remember it, but I'm calling to some common sense. I mean, this is a security course. It doesn't matter if it is AI security or any security course. You exchange information, so you have an attacker, you have a victim. So by definition, the victim is the server that trains the model. What attacker can do? So, what it can do?
The attacker can slightly change the input vector.
Yeah, for example, yes, and it will, what it will change? It will change the so when you change the input vectors. Well, maybe again. So I will extend your answer to a more general one. So an attacker may fake data, like all data that it has. It could be fake. Why? Now it's question back to you. Why would I do that? Guys, it's a simple question. So why would I fake data? So we are in a distributed learning context. As I said, we train the models partially so that at the end we want to have a global model that is rich in information. If I fake the data on my end, what is the effect? Exactly. I'm attacking the main model. As an attacker, I want to harm a main model which will be used for something useful thing.
So is that the poisoning?
For example, it's a data poisoning. It is called data poisoning, but locally. So you train your local model on, say, fake data, or you can, I mean, here there are different options as an attacker. What you can do, for example, you can think in the line of adversarial attacks, that you modify input slightly so that I mean it produces wrong classification. So why would you do that in the distributed learning? Is that probably you want to insert a backdoor so that later on when the model is trained and you know it is deployed in reality, you send a special input and it does something bad because you train it in this way. But you can, I mean, you can do data poisoning just by training on totally bogus data. Why would you do that? You simply want to, I mean, it is called denial of service attack. So you want to model to be poorly trained, so it would be underperforming. So all types of attacks that exist in, I mean, for a general IT system, so it's valid even here. You just need to kind of tune to what, I mean, you need to think about it from the point of view of usefulness of this model. But I want you to even mentally to take next step in this discussion. I mean, why bother training model on bogus data? Because, I mean, if you at the end communicate matrices, you can simply fake these matrices, the weights that you so you send fake models, or maybe I mean you can send random models with, say, big updates, large updates by the magnitude. You can send updates that reverses the sign of the training, so that, I mean, when added to the main model, so the model diverges with respect to loss, not converges, so not minimizing the loss, but making the loss bigger. So then, in either case, the network produces wrong results. And now we come, hopefully, to the definition of the problem. In all these cases, so you can at least, I mean, now if you formalize the problem, so on the one hand you have a valid data that results in valid models, and on the other hand you have bad data, either fake or modified using adversarial attacks, but these are bad data which result to the bad model. Now we'll repeat the same statement again, but from the point of view of or in mathematical terms of distributions. On the one hand, so all your data follows one distribution, which is good distribution, so that you have, for example, so take MNIST, for example. You have typical ways of writing 7 or 3. So that's what I mean by the distribution of features, at least on the, I mean, if we talk about the input. But you can talk about distribution in general. For example, distribution of final weights after training on good data. So typical statistics on the weights. So for a good data, you have certain distribution of weights values, okay? And obviously, when you train it on a bogus data, or it in any other way modifies the model, so the weights will be of a different distribution. So in the first case, with the good data and good models, we call it in distribution model or data. In the second case, we call it out of distribution. And the task is to define if you see an update, whether a particular update can be classified as in distribution or out of distribution. And to complete the picture, so you will read the slides later on, I will give you one example. And this example is about one method to understand whether a concrete update or a concrete activation or usage of the network is in distribution or out of distribution is by monitoring the values of the softmax. So the output, the output distribution. So you put something in, and then you monitor the output distribution. That's called, so this method is called maximum softmax probability. And again, on a very simple example, so you can, I mean, you can take your time and read it. For example, you have a network, so a much simpler network that has 3 outputs. So not 10 or whatever number I have on this picture, but 3. And these 3 outputs, they are computed using this softmax formula. So what does it mean? It means that all these values sums up to 1, and as such, they can be treated as probabilities. So basically, you select the highest probability as the answer, the classification answer. So, I'm here now when we are equipped with this basic terminology of in distribution and out of distribution. So for in distribution, so a typical softmax output would be of this kind. So the one which is kind of true class is substantially higher than value than the other 2 classes. Okay? In the case of out of distribution, so that somehow modified input, the network is such that, behaves such that the distribution is different. So it can be that a particular output, so you always can select a maximum, but the distribution of outputs is of different character. So it's just marginal difference between minimum and maximum. And that is an indication that something is wrong. So, and the whole task is called out of distribution detection. So the task in the context of security would be to get updates from the clients in the federated learning context and see whether the current update within the distribution or out of distribution that looks something suspicious, and then you take actions on that, and that's what you will do in lab 3. And now I can hand over to Mons. Okay. So just to complete my part, so here you can find another kind of modified version, and again, I don't know if you ever will use it, but so some, I think, useful information about how to highlight these differences between kind of in distribution samples and not distribution samples by means of adding this temperature parameter. But what we also want, we want to take information that is distributed or exist in all these different hidden layers, because it's a different kinds of information that is accumulated inside the network on different layers. And that what Mons will talk about is a special type of out of distribution detection, which is based on principles, on certain computational framework, which is called hyperdimensional computing. So you can read about it. So some information here. Unfortunately, we didn't have time to go through it.
I will also talk about it.
Yes, but the idea is to come up with a single representation of the entire model. So to collapse all matrices into a single vector. And by looking at this vector from the point of view of similarity measure, and Mons will talk about, decide whether a concrete update coming from client A looks like all other updates or something is wrong with that. That's what he will be talking about and explain this method on how to collapse all these matrices into a single vector. So I stop sharing.
Yes, I will share.
If I just find my...
So maybe my screen is...
No, wait. I stop sharing.
Hello.
Replace...
No, we're replacing mine.
Sorry. No, wait. How can I stop sharing? But I want you to.
I can finish.
No, wait. I know. Sorry. So start sharing.
Yeah, yes, you need to switch to my screen there, up in the.
Where? Here?
Yeah, go up a little bit. Where is Zoom?
There.
Yeah.
Yes, I say. Yes, okay.
And then make it full screen. That's possible.
Okay, good. Wait, what is that?
Oh, it's my screen. It's fine.
It's yours.
Yeah.
Right.
So let's see if the technology works. I will. Okay, so basically, I will elaborate a little bit further of what Evgeny talked about previously with the out of distribution detection. But in this context, we will basically apply it to a federated learning setting, which you guys will be doing in Lab 3, basically. So to sort of introduce you to the problem is that in today's society, we see an increase of machine learning and data-driven models. And we have federated learning as an emerging framework where we can distribute deep learning models to clients. So basically what we can enable is to collaborative train on participants' own private training data. And like Evgeny talked about previously, is that we have different clients who train on their own private data. And we have a server that coordinates and shares this information between all the clients. And I will elaborate a little bit further what that means later in this presentation. But in broader terms, what it means is that basically what we do is we take the model to the data instead of the data to the model. So if we look at an example, for example, at a hospital where we have 3 hospitals with confidential patient data. This patient data can, for example, be classification on whether a patient is sick or not. So what we decide to do is to train on their patient data, the patient record, which is, of course, by an integrity and confidentiality is we need to maintain it. We can't really send patient data out to ChatGPT. I mean, if we would do that, that would be harmful for the patient themselves. So basically what we do instead is that locally we send out different model or agents which trains on these hospitals. And what we do later is that we take this model that trains on the hospital, and one can say that we aggregate it into the global model.
So kind of like synchronizing with the global.
Yes, exactly. So we have, for example, 3 hospital. All this knowledge that is trained on these 3 hospital is combined in the global model. And the global model sort of keep tracks of all the different trainings that is done on the local models. So to sort of clarify the terminology here is that we have a global model coordinating and keeping track of all the work that the local model does, basically. So one problem with this is clients and auto-distribution data that Evgeny was talking about earlier. So basically what happens if we have a new hospital, hospital 4, or hospital D, for example, which starts to insert malicious data or train on malicious data, and then send this weights to the global model, which then gets sort of aggregated into the global state. I mean, the direct conflict of this is that we get a model that starts to behave outside of the behavior we want it to, if that makes sense. And this is, of course, this is what it means is that it harms the global integrity of the collaborative process. And we have quite a high risk in high stakes applications where, for example, we can start to receive misdiagnosis of hospital patients if, I mean, if they start to train on CFR10 dataset instead of training on the patient data. So basically, we want to have inclusiveness and robustness through secure collaborative training, and therefore we want a way to sort of remove this out of distribution features that we don't want the model to learn. Oh, sorry, there. So sort of the goal that you would do in lab 3, I will talk about this also next week on Monday, where I will have an introduction to what you will do. But also basically what will be done is you will create a local simulation environment that yield reliable results. So you will be sort of applying this locally, this federated learning concepts, where instead of sort of having this distributed manner of a network, you will just have different models which trains on separate data. And all these model updates are based on model weights. So basically, the model weights gets extracted from the model or the local models, and then gets inserted into the global model directly. There's no network needed here, basically. You can just do this through iterative. You can just iterate through different models, basically. But also you want to design this out of distribution detection mechanism, which the main idea will be to detect anomalies in model updates by client and disregard these updates. So sort of like the criteria is what is considered OOD and what will be the effectiveness of this, which you will sort of get explained in this presentation, also need to discover yourself in the lab 3. But like I said before, no networking will be required, which conceptually will be covered through sort of the simulation framework itself, which is done locally. No model heterogeneity, basically. So you will not have different model architectures, if that makes sense. So there won't be any dimensionality differences between different models. So all models' internal hidden layer will be exactly identical, basically. And also in this field, there's some still progress to be made, actually, in this problem area that you might have, for example, model of different architectures and different hidden layers and dimensionalities and such. But one thing that one need to remember is that we have no direct access to the internal state of the client. So basically what this means is that the data itself is unverifiable. So one might think, how can we then design an auto-distribution detection mechanism when we can't have any access to the data itself? So that's where the theory part will sort of explain. So basically the auto-distribution detection mechanism will rely on internal state. But what I mean here is that, sorry, this is what. Yeah, basically, if we look in the current state of work field for all the different auto-distribution detection solutions that currently exist, we can see that many of the current sort of solutions rely on internal states. So basically, you do input comparison commonly, where you compare the you compare the model with the data. But this is not possible in federated learning, if that makes sense. So basically what I'm sort of talking about here is that only in the field of auto-distribution detection, commonly they use input to model comparison. But in the terms of federated learning, this is not possible. So we want a solution to this where we have no direct access to the data. We want to design this auto-distribution detection mechanism. So this is sort of where the hyperdimensional computing part comes in, where we have high dimensionality vectors. And you might think now, why is hyperdimensional computing here? But basically, we will use this sort of concept for the different weights. Like Evgeny said before, that you can create a single representation of the different weights. We can use hyperdimensional computing. But I will also talk more about this so you understand why we'll use it. So to sort of introduce hyperdimensional computing is that, or as it's also called vector symbolic architectures, is that it leverages high dimensionality vectors, also called hypervectors. So basically what we can do with this concept is that we can create holistic representations for algebraic operations. So like, for example, in the neural net models you have different weights and you have different hidden layers. But the problem here is that all hidden layers have different dimensionalities. So what will happen, for example, if we add hidden layer 1 with hidden layer 2? So we want to create a representation of hidden layer 1 and hidden layer 2. The problem here is we can't add them together because of different dimensionality. So this sort of algebraic operation is not possible. But what we can do is that we can use this concept to project it to the same, to a vector or onto a projection matrix. So all the different vectors have the same dimensionalities. So basically what we do is that we project it into a high dimensional space. And these different vectors can then be added together for a single representation of all the hidden layers. So basically what this means is that hyperdimensional computing is very beneficial when traditional vector alignment is difficult with, for example, weights of different dimensionalities. So you have these different operations in this concept where you have, yeah, Farouk, you can speak up.
Can you repeat the idea of the vectors, please?
Okay, so basically the sort of idea with using, do you mean like the idea of using hyperdimensional computing, or what I mean?
Yeah, because you said we have different layers.
Yes,
With different dimensions, but
yes.
Do you mean we will unify all the vectors?
Yes, exactly.
Okay.
Exactly. So you will unify all the hidden layers into a single representation. But in traditional vector alignment, this is not possible. Because if you add hidden layers of different dimensionalities, by default, this is not possible. You can't do this. It's not a permitted math operation. But what you can do is project everything to the same hyperdimensional vector space and then add them all together. So you get a trade-off where there might be some noise, but you can by projecting all the different hidden layers to the same sort of hyperdimensional space, you can add them all together to a single representation. And what I show here is the different operations that is possible in hyperdimensional computing. So you have the bundle operation where you add different vectors, and you have binding where you basically multiply, or you do, for example, projection on two different vectors. And also you have a similarity measure, which in this definition is cosine similarity, where you sort of look at the angle between two different vectors and see the difference, how different they are, basically. Yeah, so those are the important operations. Are there any questions regarding hyperdimensional computing? Do you sort of understand the idea with using it? So basically the idea, before I continue to explaining poisoning attacks in more detail, is that we have hidden layers of different dimensionalities.
You try to merge those.
Yes, exactly. I try to merge all hidden layers into a single semantic representation, or a single representation of all hidden layers.
It's just like the previous models we were trying to do that because it's not like a value because there are different.
Yeah,
like a different DNA.
Yeah, all hidden layers are of different dimensionality. So if you would try just to add all the different weights in the hidden layers, that will not be possible by math, by simple math.
Yeah. Last time, like we were looking at like those hidden layers, like within the hidden layers, there's like different, like like non-linearity functions.
Basically, what you do is you take the weights, numeric values, which sort of decide what the output of these functions are, these activation functions. So basically, you manipulate the weights in order to get your desired output from all the activation functions. So, but basically the weights in this sense is important because it's sort of, we can understand the behavior of the model by inspecting the weights, if that makes sense.
I understand, like it works like the way I would say like softmax is trying to, not that the softmax are doing, it's like trying to make things presentable, like because there are like row numbers that he's trying to make it like more presentable, understandable, and present it. But here, like the dimension was trying to also present in the set of one vector, so like having different.
Yeah, and basically, what the concept is basically to create a single representation of all the hidden layers to decide whatever the local models are malicious or not. And I will come back to this later. But like Evgeny talked about earlier, we have something called the poisoning attacks, where we want to deliberately harm the model. And why it's important to understand the poisoning attacks is because this is a threat, like I said before, in the federated learning context. And basically what you can do is do data poisoning, where you remove or edit important features of the data set. So for example, if I have MNIST data set and I have handwritten digits 0 to 9, what I can do is, for example, all the zeros, I can add a line in the middle of it. What happens here is that the sort of 0 becomes sort of an 8 instead. And what will this cause if I do? If I draw like a straight line in the middle of all the zeros, what will sort of the behavior be in the model if it starts to train on zeros, which are sort of a manipulated 8? Yeah, basically what starts to happen, it's like all the zeros it doesn't learn any zeros. And what happens if I...
Yeah, like there's no like like non-linearity, like there's no actual complex pattern, it's just one simple straightforward pattern.
Yes, I mean, yeah, but yeah, basically the model starts to forget the zeros, and it starts to sort of it also may affect the 8s it trains on, because the 0s aren't like a traditional 8. So maybe the 8 also starts to be affected by this. And also, what happens if I start to add like picture of dogs, but we only want to train of the MNIST? Well, the like direct consequence of this is that it might start to not learn the MNIST data set. It maybe starts to only learn on the dog pictures, and this is a problem. Also, you can do model poisoning, and what you do here basically is that you manipulate the weight directly inside the model. So for example, I can just multiply all the weights by 1000, just a constant number. And the problem with this is that yeah, or maybe I like choose like every weight vector, like every 10th weight vector I multiply by 1,000,000. This will also have a consequence basically. So we want to avoid this in federated learning, basically, these poisoning attacks. So it's important to understand like the theory behind poisoning attacks and what it might, how it can harm the global model and how it can like harm deep learning models in general. And also it's important to understand the frequency and number of malicious clients and also the frequency of the attacks. So what happens if I, for example, in a federated learning context, if I start to send weights to the global model very frequently with this malicious data? Like, for example, I just have a red picture, but I want all my in distribution is the MNIST and my out of distribution is just red pictures. And then very frequently it trains on like 1,000,000 red pictures. And then it starts to send this. Basically what happens is that the global model will forget about the MNIST data set and only learn on the red picture features. So in this case, we want to avoid this.
The global model actually looks at the majority of data that is from their local models and actually looks at that majority and
Yeah.
focuses on that one, except apart from the rest.
Yeah, I mean, yes, I mean, that's also a problem in federated learning. If you think of like inclusiveness, like what's the frequency of features. So basically, if there's a larger number, but this is not really it's not important for the lab, but it's an important topic in terms of federated learning. That if you have 1,000,000 of some feature in distribution and you have 1,000 of some feature which are also in distribution, basically, if you have 1,000,000 of these features, for example, zeros. If you have 1,000,000 zeros and 1,000 handwritten ones, it will overtrain on the zeros. So this is a problem also in federated learning, but it can be good to also sort of have this thought in mind that the balance in the data set is important. But there are ways to sort of handle this, but it's not really relevant to the lab 3 and the but it's an important topic. So to sort of introduce you, no, I think my screen, yeah, now it worked. So this scenario that can be used is simple image classification using a convolution neural network. And in the case of lab 3, you will determine if patients are sick or healthy. So one can think of a scenario where you want to enhance diagnostic accuracy. And basically, you want to address the concern with patient data not being shared by maintaining confidentiality, integrity of patient data. So this is sort of the scenario I will also be explaining of the theory part now in this presentation. But basically, you can harm this diagnostic accuracy through poisoning attacks and out-of-distribution data. And this is quite a versatile proof of concept, which can be applied to other different scenarios. Yeah. So basically, the full implementation can look something like this, where you select and pre-process the data sets, which I've done before, selecting the deep learning model, which you've also been doing. But now we have this sort of federated learning environment that we want to construct, which in the case of lab 3, it will only be required to have sort of a local iteration of each model. So for example, if you have your convolution neural network model of some architecture, basically what you can do is create duplicates of this model and then just have an ID for each one, if that makes sense. So you only need to build a local simulation framework and train all the different models iteratively. You don't need to have this sort of you don't need to run everything in parallel, which in the case of a real scenario you will need to do. So it can be sequential, where each model can train sequentially, and you can just use a data structure like a dictionary. So ID1 is this model and ID2 is this model. Maybe that's a little bit do you understand sort of what I'm implying? But you want to, and then also, so basically for the lab 3, step A and B is already done for you. So we only need to implement step C and D, creating sort of this local sequential simulation framework, and also designing this OOD detection mechanism to detect malicious clients. So you need to build some scenarios which are already described in the lab description, what you should do. But you want to try some scenarios where we have some out of distribution data, some in distribution data, and you want this out of distribution features to not be incorporated into the global model.
I have a question.
Yes.
By using the example of hospitals,
Yes.
you say like us as a global model, we do not know the data.
Yes, exactly.
Because of the privacy.
Yes.
So how is this global model going to detect that this is out of distribution data, like they're not supposed, they are poison or
Yeah, exactly. Yeah. Basically, I will explain it in the out of distribution step, because I will. But basically, what we will do is that we will look at the weight vectors. So we will compare the weight vectors of the global model to each local model, if that makes sense. So the global model's weight vector is basically constructed from combining all the local models.
It becomes like a reference for the local model, like.
Yeah, you have you basically, in the terms of lab 3, you can have like a list for each local model.
So this global model must have its own standard that it's there, all features that are already there, the global models, and like they have been combined from the distributed one. So when something new comes, it knows like this from this list, this is not here. Or
yeah, okay. So basically, what we do is that, for example, if we have a local model that trains on malicious data, the weight vector alignment of that local model will differ a lot to the global model. So if we have our in-distribution samples, our weight vectors will align to this in-distribution data. But if we now have, for example, so if I take this example like with MNIST and the sort of red picture, all the red pictures, the MNIST vector alignment will be similar to the features of the MNIST dataset. But how will the vector alignment of the weights be with the red picture? So if we want to sort of, if we train on the red pictures, which aren't in distribution, it's just like random samples that we deliberately want to harm the global model, the weight vector difference will be a lot different. So we want to compare the local model weights with the global model weights through the concept of hyperdimensional computing. So we create a single representation of all the hidden layers in all local models. So we have local model A with as a representation through hyperdimensional computing of all its hidden layers. So local model A, B, and C has a single representation of all the hidden of its weights. And then we compare it to the global model. So when we then do cosine similarity between the global model vector, weight vector, but in this case it would be the single representation of all the hidden layers. Basically, we can see that if these red pictures, if we do cosine similarity of the global model to the local model that trains on these red pictures, the cosine similarity will be very low. And what this sort of indicates is that the data, that the underlying data that it trains on is by a high probable cause out of distribution. Does that make sense? So we compare basically the weights. We compare the global model weights with the local model weights. But in order to do that, we create a single representation through hyperdimensional computing concept, where we combine all hidden layers and the weight vectors into one single representation. So now I repeated this concept very much, but this is like the main fundamental of the out of distribution detection mechanism that we will be designing in lab 3. So to elaborate, we have this, like I showed on the picture before, we have step A, B, and C, where we have selecting the data sets, pre-processing, and selecting deep learning model. Like I said before, the data sets, that the code that is provided in lab 3 contains all this functionality already. And basically, the data sets that you will be using is an Alzheimer data set, 2 unique brain tumor data sets, and a pneumonia data set. Where you also have all this pre-processing where you will be labeling whatever a patient is sick or healthy. Basically. So this will sort of be the data set that you will be using as your proof of concept. So in total, you have around 18,000 in distribution features. And basically what we do in order to poison this data and introduce these anomalies to the in distribution features is to basically, I think I described this but basically this in distribution features that either has the label sick or healthy, we can, for example, flip the label. So if a patient is in reality sick, we instead choose the label healthy. And this we can do manually ourselves in the test simulation for the auto-distribution detection mechanism. So when we want to train on the poison data and see how this works in reality, we can just flip the labels. The ground truth label, we can change it to the other one, basically. Does that make sense? Okay, I saw your question, Farouk. You can reduce you don't need to train on all the 18,000 features, but like we have said before in the previous labs, like some valid number, which proves that, I mean, it's hard to exactly say, but you don't need to, if your computer will explode from training 18,000 features, you can reduce it.
Can we train like 10%?
Yeah, yes, you can experiment a little bit with the total in distribution features. So I mean, there isn't a hard requirement that you need to train all the 18,000 features.
Yeah, but like in lab 2, there was a question how close our results with the paper, and we find it hard a bit to match with the paper because we don't have the same GPU and CPU.
Yeah, it's completely. I mean, if the accuracy is lower in the lab, it basically we just want you to reflect on your own implementation to see why it derivates or why it why it's different from the paper itself. And if you, for example, have had hardware problems and reduce the amount of features that you train on, this is a valid sort of discussion in your report. So you don't really need to train on all the, you can reduce the number of samples. Yeah. I just looked at the time and we have 10 minutes left, so I think I need to accelerate a bit. But basically, this is the sort of convolution neural network model that you will be provided with. But instead of using PyTorch, you will be using TensorFlow now, which is another framework. But there is already, I think, functionality in the provided code to import it. And so it shouldn't be a problem. But you can, of course, reduce the complexity of the model if you have hardware problems. But we can talk more about this sort of lab detailed discussion on Monday next week. Basically, I want you to understand the theory now for lab 3. It's the main point. So to sort of explain, we have these local models which trains on assigned data sets and model. And like I explained before, the federated learning framework that you will be designing will be local and sequential. There's no need for networking. There's no need for like model architectures that are different. But basically, the only steps that you do is that the local model trains on the assigned data set and the model, internal model that it has. And then you do aggregation, where the global model it computes an averaging weight sum of all the local models. And by what I mean with this is that you combine all the weights from the different local models. And then you do regression, where all the local models gets updated by the global model state. So local model trains, all the different training states gets aggregated to the global model, and then the global model distributes these training states of all the local model back to the local model. So local model A receives the train state from local model B, C, and D, and vice versa for all the different local models. So this is sort of the fundamental of federated learning. But all this is done locally and sequentially, so you don't need to have any fancy simulations where everything is running in parallel and you have some networking. You don't need to do that, basically. But it's also important that the global model is distinguished from the local models by some identifier or however you want to implement it. But now I'm sort of coming into the auto-distribution detection mechanism here. And what I've been sort of explaining before is that this mechanism is implemented on server side, and you do weight vector comparison through or by using HDC, hyperdimensional computing. So you compare the global model with the local model update. And if a comparison criteria is met, you include the update from that local model. And the sort of comparison criteria is the cosine similarity value. So you do cosine similarity between the global model and the update from that local model. If the value is low, don't include it. If it's high, you include it. So you can decide some threshold value between 0 and 1, probably 0.6 or something. So if the cosine similarity is above 0.6, you include it. If it's below, you disregard it. So now I'm sort of, maybe I can move this a little bit so you can see the picture a little bit better. Here is a little bit more detail what actually happens with so basically you have a deep learning model to the left with an input layer, hidden layers, and output layer. So you have a projection matrix of some hyperdimensional size. And then you project the feature vector, or in this case, the weight vector of that position. So basically you project feature vector 1, which is hidden layer 1, all the weight vectors in hidden layer 1, onto this projection matrix. So basically what you do is you bundle then these projected vectors and create a holistic representation of model X, which I explained before. The single representation of all the hidden layers. And this results in a class descriptive vector of all the different models. And like I also explained, you have this cosine similarity value where you measure between the class descriptive vector, and the class descriptive vector is the single representation of all the hidden layers added together. And then you see if it's close to 0, it's out of distribution. If it's close to 1, it's in distribution. And this threshold value, like I explained before, you decide what value is appropriate, basically, and if it should be disregarded from aggregation. So basically here I have a summary sort of all the steps that this sort of simulation will cover, and what the fundamental idea is of each sort of step, where you basically, let's see if I can see my mouse pointer. Yes, you have global regression. So for example, we start at round 1, for example, epoch 1 or round 1. We first distribute the global model weights across all local models, basically. You create this class descriptive vector for the global model by using this projection matrix and the features extraction, which is all this hidden layer for the global model. And then for all the local models, you then do training based on some simulation parameters, which are described in the document, in the lab description document. And then you train for all different participants on this data that you can select. And then you do feature extraction, similar what you did up here for the global model. And then when all the local model has trained on its own data, you then project onto this projection matrix, you compare it through cosine similarity, you select valid models for aggregation that should be combined into the global model based on this threshold value. And then you combine it. And then you repeat this step over again. So this is the steps, the method basically that the simulation should cover. So now I want to show a little bit fast, since we have 3 minutes left, the different some evaluation examples, which are done. So basically we have done simulations on this previously. And this is basically, you should reflect on this, because similarly you should recreate this in your lab 3. So as an example, we have this scenario with the sick, healthy patient data sets. What we do then is that we do pre-training on all the in-distribution features, where we train, for example, 30 rounds. So we only train all local models on the in-distribution features for 30 rounds. After that, we do another simulation scenario where we add a malicious client with out-of-distribution samples. What we do then is that we can inspect the global model's performance, in this case the test accuracy of all the in-distribution features that we use in training. And also what we can do to evaluate the success rate is to look at the cosine similarity plot. How different are the local models to the global models? And here are some examples of the sort of parameters that are used in simulation, where you have the global model with ID0, for example. You have all these in-distribution features, 18,000 features. You have local model 1, training on the brain tumor 1 dataset, which are 4,600 features. You have all the different datasets assigned to each local model. But then for local model ID5, you have the Alzheimer poison dataset, which are label flipped. And then you train on these 1,000 features And for example, here we have a OOD threshold value of 0.5. So if the cosine similarity is above 0.5, we include it into the global model. And these are some example simulation parameters. You don't need to replicate this exactly, but there are some like skeleton for this already in the code. But you don't need to show the ROC and AUPR score for lab 3. You only need to show the cosine similarity plots and global model performance. So for example here, for 4,600 malicious samples. So now we have pre-trained before on 30 rounds on all the in-distribution features. But now we have a new malicious client with 4,600 malicious samples of the Alzheimer datasets. So all features in the dataset are label flipped. If a patient should have been sick, it's instead labeled as healthy. And basically what happens, well, if the OD detection is enabled, we can see a growth in test accuracy of the global model. But what happens if we disable it? Well, we can see that the test accuracy starts to, it doesn't converge towards a good high value or towards 100% accuracy. Instead, it's sort of decays and starts jumping up around 0.87% or 87%, sorry, which is not good. So here we can see how the success rate by enabling the OD detection mechanism. But I want to show you this before I show this. So now what we do here is that we do exclusive training only on the malicious client. So now we remove all the local models that train on their own in-distribution dataset and only have the global model and the malicious client. Well, what happens now if we disable the OD detection mechanism? Well, we can see a drop of the test accuracy. Basically, the global model tests on the in-distribution data that was used previously in pre-training. But now, since the malicious client is only training on out-of-distribution data, we can see this drop of around 40 or 50% after only one round of training. So here we can see the problem. What happens in a sort of federated learning scenario when we have this out-of-distribution data. But I want to go back a little bit to here, where we have these cosine similarity values. So we have local model with ID 5. This is the out-of-distribution client training on out-of-distribution features, malicious features. And we can see this separation of in-distribution features, local model training on in-distribution features and local model training on out-of-distribution features. And this is something we want to achieve, to separate the local model, which is training on malicious samples, from the healthy clients. But when we then disable it, we can see that it sort of it's the local model that used to be out of distribution is now in the same sort of not distribution, but in the same similarity value. So basically the global model starts to learn on the out of distribution features. This is some other benchmarks, but like this part, but you don't need to show the AUPR and ROC scores, but this was from the scenario shows before. So you don't need to show the ROC and the AUPR values. You only need to have the cosine similarity plot and the accuracy plots. So I can do like this. I can upload this presentation to Canvas since we are 5 minutes overdue right now. And then there are some other scenarios which you will be conducting in lab 3. And basically the scenarios you will be conducting are the ones that are shown here. And these are somewhat the results you should approach. But since you might tune the network to meet your hardware requirements, and you might not train on as much in-distribution features, there might be a difference in accuracy and such, but that's no problem. But then reflect on it. So yeah, there are some other examples here, for example, where you have a completely new animal face data set. And you can see here that we can detect it basically. And yeah, so that's it. Are there any questions? But basically, like I said, this is sort of the theory for Lab 3, and there are more details in the document. And there is also a template for the code, but I will talk more about this on Monday. Maybe you have some more questions then on the theory also.
I have a question offline.
Yes. Do you mean offline in like a private question, or?
No, like now after the recording is stopped.
Okay, absolutely. But yeah, however, thank you everyone. And the lecture is done. Now I should see if I can. Oh, wait. Stop share. I should see if I can disable the recording.